A traditional cargo ship takes 18 months to build, yet an engineering team managed to construct 9 of these 400-meter eco-friendly megaships in 2 years. To achieve that kind of speed at this scale, they had to throw out the standard rulebook for shipbuilding. This timeline comparison illustrates the core problem. The top half is standard frame building, where a single hole creates a massive bottleneck because only one team can work on the keel at a time. The bottom half shows the solution: modular block construction. Multiple, independent sections are built simultaneously in parallel. The process begins with industrial lasers, running at 18,000 degrees Celsius, to slice exactly 12,660 flat steel sheets. These sheets are then welded into 3D room-sized blocks, complete with internal piping and wiring already installed. To build a vessel of this size in record time, you completely abandon linear construction. Instead, the entire operation is decentralized, spreading dozens of these pre-fitted blocks across a sprawling 4-kilometer-long shipyard. Moving these massive modules into position requires immense mechanical force. A single stern block weighs 790 tons, requiring twin giant cranes operating in perfect synchronization just to lift it off the ground. Once in the air, the physical constraints for placing the block drop to zero tolerance. The cranes must lower the module with such exactness that a single millimeter of error will ruin months of meticulous preparatory work. This map visualizes the staggering scope of stitching those perfectly placed blocks together. Workers complete 1,250 kilometers of manual welding. If you laid every weld in a single straight line, it would stretch all the way from Karachi to Lahore. Every inch of that 1,250-kilometer seam is heavily scrutinized. Flawless, continuous welding provides the only structural defense the ship has against the immense, fluctuating hydraulic stress of heavy ocean waves. Powering this vessel requires moving away from traditional heavy fuels and utilizing liquid natural gas. This introduces a major friction point: safely storing 20 million liters of liquid gas at an extreme negative 161 degrees Celsius inside an 18,000 cubic meter tank. Before final insulation, the tank must be 100% airtight. How do you find a microscopic leak in a 6-story tank without filling it with liquid? Engineers apply a simple soapy water solution to the external joints and place a glass container over them. A compressor is then used to pull a vacuum. Any microscopic gap allows external air pressure to force its way in, instantly creating visible soap bubbles at the exact site of the weak point. Once sealed, they face a final thermal threat. Standard rigid steel cracks when exposed to negative 161 degrees. The solution is a 1.2 millimeter steel membrane stamped with a wavy pattern. As the extreme cold hits, the metal physically contracts and stretches like an accordion, absorbing the thermal shock without fracturing. Managing extreme cryogenics safely requires abandoning the idea of building stronger, rigid walls. You have to engineer materials that yield to thermal physics. Driving this hole through the water takes an 85,000 horsepower engine. Getting it to the shipyard is a logistical hurdle all its own. The crankshaft alone weighs 220 tons and has to be rolled in on highly specialized 140-wheel platforms. The final mechanical hurdle is attaching the 92-pin solid cast propeller to that crankshaft. At high RPMs, a microscopic misalignment between the shaft and the propeller housing will trigger severe mechanical vibrations, tearing the engine apart. This diagram illustrates how engineers prevent that failure using the blue dye test. They coat the entire shaft in bright blue dye and insert it into the housing. When withdrawn, any bare metal patches clearly map out the exact points of high-pressure friction, telling the team exactly where to grind down the metal for a perfect fit. A modern ship relies on thousands of digital sensors, yet preventing catastrophic mechanical failure ultimately comes down to a purely analog, manual friction test. With the hull and propulsion systems complete, the exterior receives specialized paint. This acts as a chemical barrier against salt corrosion, while physically smoothing the surface to reduce water friction, visibly lowering the ship's total fuel consumption. Up top, the command bridge is installed. Featuring a Smart Eyes 360-degree digital camera array, it functions as the central nervous system. giving the crew complete control over the 400-meter structure. Finally, the ship undergoes 15 days of grueling sea trials. Engineers push engine thresholds to the red line, execute emergency braking maneuvers, and deploy an anchor system so massive that a single link in its chain weighs 300 kilograms. Clearing these trials serves as the definitive real-world proof of concept for low-carbon, megascale global shipping.
This blueprint
Summarizes the core solutions: parallel modular construction, flexible corrugated membranes, and analog die testing. Building at the megases. By perfectly managing 1mm welds, tiny thermal sips, and exact friction points, engineers assemble the large